All right, students, it's now time to enter the next chapter of our textbook, Chapter 4. Chapter 4 deals with some really important fundamental concepts in chemistry. The first of which we're going to talk about today, is writing and balancing chemical equations. And the second real large topic in Chapter 4 is stoichiometry, which includes the concepts of limiting reactant, theoretical yield, and percent yield. So let's get into this main topic first, writing and balancing chemical equations. So now that you all have mastered how to write chemical formulas for a bunch of different compounds, whether they're ionic or molecular compounds, otherwise some schools call these covalent compounds. Molecular, covalent compounds, same thing. Now that we have that knowledge, we can kind of progress into writing chemical equations. So essentially, all that a chemical equation is, it's just basically describes a chemical reaction. A chemical reaction. And a chemical reaction, once again, always has the basic format of reactants, which are basically the chemical species before the reaction. So in other words, what you have at the beginning, and then an arrow to indicate there was a chemical reaction occurred. And once again, a chemical reaction just means that atoms that used to be joined together will split up and rearrange with new partners, and you'll create new things. And those new things are called products, which is the chemical species, the types of compounds that you have after the reaction. And all that the chemical equation is just writing it in this format. What you have at the beginning, an arrow to show that things changed, and now what you have on the other end of it. So the concept here is fairly simple, is we just have to turn a chemical reaction into this chemical equation. Now, the key here is this, the part that can trip people up a little bit, is balancing the chemical reactions. So let me go ahead and put up a chemical reaction that exists or that occurs in nature. Okay, so we have a compound called CH4. By the way, CH4 is a famous compound that I would like you to know his name. His name is methane. He's a classic Gen Chem 1 compound because he's small and he's really important. So methane. Methane happens to react with, and that's what the plus sign means. It means this reacts with that. Okay, when you put them together, they'll undergo a chemical reaction. And it happens to create, when they meet, it happens to undergo a reaction where the atoms will rearrange, get new partners, and you're going to form carbon dioxide and water. So this is a chemical reaction that occurs. Methane reacts with, notice the words that I'm using, methane reacts with oxygen. Remember, that's a diatomic element, so he's O is O2, to yield. Okay, by the way, the arrow, it's fine to say to yield. It's fine to say to make. It's fine to say to produce, or whatever. There's lots of different ways to say it. There's not just one right way to say it. It all means the same thing. Carbon dioxide and water. Now, here's the part about the balancing. Remember that matter can neither be created nor destroyed. Whatever amount of matter that you have at the beginning of a reaction has to be still present at the end of the reaction. So when you think about these as atoms, which they are, okay, a CH4 has 1 carbon atom and 4 hydrogen atoms. So when you look at it as it's written, where you just have the chemical species written down here, you can see that right now it appears that yes, carbon, the 1 carbon atom is still present on the other side. So that's good. We have to have it. It can't just disappear. It needs to still be maintained. But you can see here that the 4 hydrogen atoms that were present on the front end of this reaction seem to have disappeared. We only have 2 hydrogen atoms here. So essentially, right now, what you have is an unbalanced chemical equation. So it's unbalanced. when you have different numbers of each type of atom on either side, or at least one of the types of atoms on either side. It might be balanced in carbon, but we can see it's not balanced in hydrogen. So if something's off kilter, if they don't match, the numbers don't match, it's not balanced. And that is a big deal because that violates the law of the conservation of matter, which means that doesn't actually happen. So what we have to do is we have to balance this chemical equation. And all that balancing means is that you have equal numbers of every type of atom on both sides. Now, here's the deal. One of the temptations could be to go and fix this and make this a 4. Because you would say, well, now I'll get the 4 hydrogens on both sides. But clearly, that's not allowed because this reaction doesn't make a molecule called H4O. That doesn't even exist. The reaction makes H2O. And by the way, how are you supposed to know that? At this point, you're not really supposed to know that. That would have just been told to you. The reaction is producing water. So one of the main points about balancing chemical equations is that you cannot touch the subscripts. You're not allowed to change any subscripts because that would change the species itself and create a fallacy that doesn't exist. The only thing that you can change are what are called coefficients. Coefficients are the numbers that go before the chemical species. Now, I'm going to draw lines here just to make the point. I don't necessarily recommend writing that in your work, but that's really what these are. These are called coefficients. And they tell you the number of each type of species that is present in your chemical reaction. If you don't see something written there, it is implied to be a 1, just like I inferred it earlier, is 1 methane molecule. So the only thing you're allowed to do is change those. So when you look at this chemical reaction, let's see if we can balance it. And the tips to balancing, let me go ahead and give you a couple tips. There's several tips, and I'll keep adding them as we need them. But number 1, this is a big one. Use pencil. You've got to trust me on this. If you are using a pen, now this one's going to be easy. Many of you probably can tell right away where I'm going with this, but they will get harder. And it is a very bad idea to use pen because pen is not going to erase and you're going to end up crossing it out and you're going to end up getting really confused in your mind with what the numbers should be. That is a huge thing, is that you should use a pencil so that you can erase and start over. The second thing to recognize about balancing is that it is a trial and error process. If you are trying things and it doesn't work out, so you erase and try again, you're doing it correctly. That is how everybody does it. So it is a trial and error process, but you have to know where to start. And what I always tell people is just start somewhere by fixing any one of the atoms. Now, as you get a little bit better in it, you might get a little bit of wisdom as to where to start. But honestly, the best thing to say is this. Don't have paralysis by analysis and say, I don't know where to start. Just fix one of the atoms. So for instance, what I did earlier, I looked at, oh, and by the way, some people do this as well. They make a list of all the types of atoms that exist on either side. Or so it's going to be the same types on both sides because it's not just going to appear a new type of atom. So there's carbons, hydrogens, and oxygens. And you'll note that right now there's 1 carbon on either side, okay? So carbon is balanced. You can do it kind of like that to keep track. Right now there's 4 hydrogens on this side and 2 on this side. If you want to do this, it can help some people. So you can see hydrogen is not balanced. So how can you fix it? Just put a 2 right here, and that will give you the correct number of hydrogens. Now you're going to have 4 hydrogens, okay? And now go ahead and take a look at what happened to oxygen. See, if you change hydrogen here and make this 2 waters, you do fix hydrogen, but don't forget that will also get you 2 more oxygens as well. So total oxygens now is 2 plus 2 more, because sometimes the oxygens are deposited in different places. You got to make sure you count both. So I've got a total of 4 oxygens on this side. And how do I get 4 oxygens on this side? Well, you would just put a 2 in front of here. And so this little process here in the middle, this thing here, I would say that it's fine when you're first learning how to balance an equation. I will tell you that as soon as you can do this whole thing in your head, you will be better off. You, at the beginning, just to get the hang of it, maybe, but try to get to the point where you can just kind of go back and forth. And really, it's just a matter of going back and forth until all the different atoms are balanced, and then just make sure. 1 carbon on both sides, yes. 4 hydrogens on both sides, yes. 4 oxygens on both sides, yes. And then you're balanced, and that is a balanced chemical equation. So let me put some more up here. Just to have some, because there's a few more tips that I want to be able to include. Let's go ahead and say, let's do this one here, KClO3. And at this level, all that we're doing is I am providing the chemical species. I'm telling you, it's not like you have to know what this makes. You know, that's not something that you would be expected to know when it reacts, or again, in this case, it would be decomposing, breaking down. But if someone tells you what the two products are when it decomposes, okay, you have to go ahead and balance it. So you can pause the video if you want, but I'll talk you through how to balance it. So once again, use a pencil and just use trial and error and start somewhere by fixing somebody. So I just go to where your eyes look. I see potassium. Right now, potassium looks good. I've got 1 on both sides. So I'll move to a different atom, chlorine. Right now, chlorine looks good. I've got 1 chlorine on both sides. But how about oxygen? Well, there's 3 oxygens here, and there's 2 here. That is not balanced. The key here is that when you're trying to marry a 3 and a 2, the only way that you're going to be able to get the same number on both sides is to have 3 copies of the one that had 2 and 2 copies of the one that had 3. That will end up getting you 6 of both, and that's the only way you're going to get a 2 and a 3 to match. So, but notice, now oxygen's good, but that ended up changing the potassium now. So you have to basically readdress the potassium. So you kind of have to just like follow it to where it leads until all of them are good. So, now that I have 2 potassium atoms, I'm going to have to now fix that with the 2 here. And that will give me my 2 potassiums. And then the 2 chlorines, because remember, if I've got 2 KCl molecules, I mean, they're not molecules, they're formula units, but just think of them as a molecule. If I've got 2 of them, then I have this and I have another one. So that gets me 2 potassiums and 2 chlorines, okay? So anyways, I put a 2 right there to fix the potassium, and then you can see the chlorine is also fixed as well. So this equation is now balanced. Okay, so let's keep going and do a few more here. How about, let's do this one, C3H8 plus O2 yields CO2 plus H2O. This is also a similar type of equation to the earlier one that we did. It's actually a combustion reaction. The one that methane was kind of similar. You notice it reacted with oxygen to make these 2 guys. Let's see if we can balance it. Now, I'll give you a little clue. On combustion reactions, and we'll learn a little bit more about those later, but ones where you've got like carbon-containing compounds reacting with oxygen to make these 2, they're kind of a famous type of reaction. Always save the oxygen for last. One other tip is that it's not a bad idea to save simple chemical species for last. The reason I say that is because when you go to put whatever here, it won't end up changing anyone else. So it's a good kind of final step. It's not like going to create a new problem. So maybe save him for last. So let's look at carbon and hydrogen. I see 3 carbons. So the only thing I can do to think right now is get 3 of those. That will fix the carbons. Let's look at the hydrogens. I've got 8 hydrogens. How can I get 8 on this side? Well, each copy of water gives me 2 of them. So I really only need 4 waters. Okay? And now I've got how many oxygens? Well, I've got 4 oxygens plus 6 more. So that's 10 oxygens. And that would need a 5 right here to balance out. 5O2, that will get me my 10 oxygens. And notice I'm kind of doing this all in my head, and that would be the goal, is to see if you can kind of just account for everybody in your head. Let me do another one here, which will give me another tip to give you here. Mg, NO3, 2, so hopefully you know that his name is magnesium nitrate, reacts with potassium phosphate to yield magnesium phosphate. Hopefully at this point the formulas make a lot of sense to you. You know why there's a 3 there and why there's a 2 there. You know that. Plus potassium nitrate. Okay, here is a really good tip. So good, I'm going to star it here. If you see polyatomic ions on both sides, like the same ones. So what do I mean by that? You see nitrate right there, the NO3 ion, the NO3 minus ion. See how he's still present over here? And you see phosphate, PO4, 3 minus. See how he's present over here? It's not like they broke up. They're maintained as a chunk. Still there. There he is. He's still there. So if you see them on both sides, treat them as kind of like a whole unit, as whole units, as chunks. Don't break up the atom, or don't break them up into individual atoms, because if you do that and you break up and you start counting nitrogens and oxygens separately, you're going to have to go add his oxygens to his oxygens, and it becomes a big accounting mess for no reason. It's way easier to just think about the polyatomic ions as a chunk. So you want to pause the video, see if you can balance this, and I'll go ahead and do it myself. So what do I see? I'm gonna, like I said, start somewhere by fixing somebody. Don't overthink it. My eye went here. My eye just went here. Magnesium, there's 3 of them. Okay, remember, this one applies to who's directly in front. That one applies to who's directly in front. All right, there's 3 magnesium, so I'm going to put a 3 right here. That fixes magnesium, because this one only has 1 magnesium, so I would need 3 copies of this molecule. Remember, the only thing you're allowed to change is the coefficients. Okay, and then I just basically, I just do who's ever next. So if I had just fixed magnesium, and I did, now I'll deal with the nitrate. He's just right next to him. So kind of follow the path just as it naturally leads. Now, how many nitrates do I have? Remember, you're considering this as a whole species, the NO3. Each one of them has 2 copies, two nitrate copies, but I've got 3 of the compounds. So that means I have 6 nitrates. How do I get 6 nitrates on this side? I would need 6 of these. 6 of the potassium nitrates, because each of them only has 1, so that I need 6 copies. Now I have 6 potassiums, so you just go to whoever's nearby. 6 potassiums. How can I get 6 potassiums here? Well, this compound has 3 potassiums, so I would need 2 copies of it. That gets me 6. And then how many phosphates do I have? Well, if I have 2 copies of this, I've got 2 phosphates, because each one of them only has 1 of them. So now I have 2 of them, and that will be balanced. And usually, if you've like fixed 3 of the 4 things, the 4th one, like it usually it's pretty obvious what to do. So that's a big one. If you see the polyatomic ions, don't separate them out. And so let's go and extend this a little bit farther. I'm going to actually leave these tips here because I'm trying to remember, I might want to add more. Let me just see. Let me see. Yeah, let me do this one here. So a couple little details on here that weren't present before. And as you're writing these down, you want to get to the point where you actually can name them pretty well. So this would be cobalt-3 nitrate, because I know that this is the cobalt-3 plus ion, because it needed 3 nitrates to balance it out. This would be ammonium sulfide. Notice this time I'm giving you phase labels, okay? You are not necessarily required to have known that those were both aqueous, but if someone tells you don't lose the information, just keep it in there. Aqueous, by the way, just means dissolved in water. All right, and then this, that makes this compound CO2S3, so that would be cobalt-3 sulfide, solid, and NH4, NO3. So this is if someone gives you this, and he's aqueous. If someone gives you this chemical reaction and they're asking you to balance it, that's kind of where the level that we're trying to accomplish here. So what I want to show you is this. I told you start somewhere by fixing someone. If your eye takes you to ammonium first, just by chance, I see that there are 2 ammoniums here. So I'm going to fix ammonium by adding a 2 right here. Okay? And then, so that says 2 NH4NO3. Then I see that there's 2 nitrates, 2 NO3s. Now I come over here and I'm like, uh-oh, there's a 3 right there. How am I going to get a 2? The next tip that I would write is, if you hit a brick wall and you feel like things have gone astray and you just don't know what to do next because it just feels off and you can't figure it out, just erase and begin with someone else. Begin with a different chemical species. Okay, that's just really good advice. Like here, it just didn't work out for me. There was 2 nitrates. I'm trying to get 3, and then it feels like it's going to just erase it and say that didn't work out. Let me start with somebody else. I'm going to start with, let me start with cobalt. Okay, there's 2 cobalts. All right, let's see what happens. I'll put a 2 right there. That fixes cobalt. Now I'll fix nitrate. Now there's, this makes it 6 nitrates. I can get 6 by doing a 6 over here. That gets me 6 ammoniums. I can get 3 over here. And then that gets me 3 sulfurs, and that works out perfectly. So sometimes, I mean, we could have kind of worked the other one out by fixing a few things, but sometimes the absolute best thing to do, just mentally, is just say, okay, that wasn't easy. So just kind of erase it and start in a different place. Because sometimes it's all about which one you pick first. What, you know, will be one that's kind of easy. It'll just kind of fall into place easier. You see how that kind of fell into place a little bit easier. So that's another good advice. It's just, you know, if it's not feeling easy, erase and start with a different one. You'll notice that you are not allowed to use fractions, okay? So they've got to be whole numbers. You notice I'm not trying to do 1/2 or anything like that. There are some techniques that people will teach to, you know, do fractions and then multiply them all at the end, and I just think it's a bad idea. I don't like teaching it like that. I think students get super confused when you do it like that. So don't even go there. Don't try to do fractions. Just to try to make it work. Just you know, always just erase it and start with a different one. Let me see if I can think of an example where you would be tempted to do the fraction thing. Yeah, okay, how about this one? This is a little bit harder. C8H18. So this is octane. This is another one of these combustion reactions, but these are famous, so you might see these quite a bit. Let me talk you through what's going on with this one, okay? So remember I said do the oxygen last because he's simple, like he's only one type of atom, so maybe save him for the very end. That's pretty good advice. So let's deal with C and H. 8 carbons. Let's put an 8 right here. That fixes carbon. 18 hydrogens. How do we get 18 hydrogens? 9. That gets us 8 hydrogens. Now, how many total oxygens do we have? Well, let's see. I've got 9 from him, and I've got 16 from him. So that's 25. 25 total oxygens. Some people would be like, oh, if I put like a 12.5 here, or a 12.5, which is the same thing, then I'll get 25. And then I'll just, really what you would have to do is you would have to times all the coefficients by 2 to get the final answer. I think it's a bad idea, okay? I don't think that's a good advice because I think people forget what to do and they oftentimes make mistakes. With This is what I would consider almost like a brick wall situation where you can't get it to work with a whole number. I would say erase it, erase everybody. And basically what you just found out is you weren't able to balance it with only one of these. It didn't work. It didn't lead you to a solution without that didn't force you to have a fraction. So essentially you just proved that there's not only one of these in the chemical reaction. So go a little higher. See what happens when you do two of them. See if you can balance it. So now we've got 16 carbons. I can do that right here. We've got 36 hydrogens. We can do that with let's see here, 18 gets me 36. Now 18 oxygens and 32 oxygens is 50. And I can get 25 here. And then you're balanced. So that's kind of another little advice thing. If you've kind of proceeded all the way to the end and it didn't work with only one of especially these hydrocarbon type of chemical reactions, try two and see if it works, okay? Alrighty, so that's that. Now, I think that's enough tips for balancing chemical reactions, but now we want to kind of take this to a little bit of a higher level. That was a situation where I give you all the chemical species. The next kind of layer on top of difficulty is when someone gives you a verbal description of a chemical reaction, and you have to turn that into a chemical equation. So let me go ahead and kind of give you a practice question here. If someone says nitrogen reacts with hydrogen to produce ammonia. Notice the difference. Now they're giving you like a sentence, words, but you still would be required to turn that into a balanced chemical equation. So what you're going to have to do is all of these names have to be turned into chemical species with symbols and subscripts and numbers and stuff like that. Once you get them all into place, then you balance it. That's so essential. Don't try to balance it until you get everybody on the paper, because you're going to mess it up if you try to jump the gun and balance it beforehand. Okay, so all you have to do is think, what is the formula for the first species, nitrogen? Nitrogen is a diatomic element. You have to remember he's N2. Now, if no one told you the phase, then you're not required to know the phase, so you just skip it. A lot of times the phases are not important for what type of question you're being asked. Sometimes they are, but frankly, they would tell you what the phase was. No one just knows what phase everything is in, because everything can be every phase in different temperatures and pressures. So you don't just invent phases. So unless you're told, just leave it out. So nitrogen reacts with, that's what that means. Hydrogen. Hydrogen is another diatomic element. In other words, it's not going to say dihydrogen, but you have to know that, remember there were 7 of them, 7 diatomic elements, that if you're just talking about the element nitrogen, you have to remember that he was a molecule, a diatomic molecule of 2 of them. To produce ammonia. Now ammonia, you just have to know it. That's on your list of must memorize species. He was one of on the list of bases. All right, so now you've got your chemical species on the paper. Now you balance. Okay, so first get them on. Now, start anywhere you want. 2 nitrogens. Let's fix that first. Okay, that gets me 2 nitrogens. Now, how many hydrogens do I have? I'll now have 6, and there we go. That will get me 6 hydrogens. Let's see about doing some more of these here. So how about a little bit different wording. Sodium hydroxide is produced by the reaction of sodium oxide with water. Okay, and then the question would say, write the balanced chemical equation. So you really have to be, you can't be too robotic about it. You have to do what it says. sodium hydroxide is produced. So is sodium hydroxide a reactant or a product? Well, clearly it's the one being produced, right? Isn't that what it says? So sodium hydroxide. Now, we have that on our list of bases as something that you've memorized, but frankly, if you just remember hydroxide is OH minus, the polyatomic ion, and sodium, when it's paired with an ion, with an anion, is going to be the cation. The cation form of sodium, which is this. You'll know the formula. It's just one sodium for every one hydroxide. So it's produced by the reaction of, so that means that these were the ones that were reacting, or the reactants. Sodium oxide, Na2O, because once again, metal, non-metal. So that means it's ionic, but that means they're ions. So oxygen is the O2 minus. Sodium is the Na plus. That means you need 2 of these for every one of this to get neutral. So that's sodium oxide and water. Water is just old-fashioned H2O. Okay, now you balance it. All right, start wherever you want. Now, what I would do is start with, well, I guess I was just going to start with whatever one you see first. That's what I would say. I saw sodium first, Na2. So how do I get 2 sodiums? Put a 2 right there. That fixes the sodiums. Now, let's go to, here's the thing. Oxygen is kind of implanted in 2 different species. So let me look at hydrogen next. 2 hydrogens, okay, on this product side. So go over and check the reactant side. It's just a back and forth. Just they got to both be the same numbers. 2 hydrogens, and there's your 2 hydrogens right there. And how many oxygens? Well, 1 from him and 1 from him is a total of 2 on the reactant side, and there's 2 on the product. So that was pretty easy. Let's go ahead and do a couple more. How about, let's try this one. Zinc reacts with iron 2 chloride. Oops, sorry, iron 3 chloride. Yielding zinc chloride and iron. Okay, so that is the sentence. We're turning that into a balanced chemical equation. All right, zinc. Well, that's just an element. It's on your periodic table. It's the name of an element. Now, it's not one of the diatomics, so therefore by default, just consider it an atomic element, which means all you do is write the atom, zinc. Reacts with iron 3 chloride. Remember, the iron 3 is telling you that it's the 3 plus ion of iron that's in there, the 3 plus cation. Chloride, we know, is when it's an ion, is OCl minus. So how many of each do you need? Well, you would need 3 of the chlorines. Of the chloride ions to balance out every one of them. And that is the formula unit that would be neutral in that lattice structure. So notice I'm not writing any charges up here. Everybody knows they're there, but you don't write them in. Yielding, that's code for that. Yielding, or producing, or making, or whatever, forming, whatever verb you have. Zinc chloride. All right, now zinc is kind of an interesting one because it is a transition metal, but I told you in one of the videos that there's a couple transition metals, actually 2 of them, that always, well, there's a couple more, but with the ones that we want to memorize, the famous ones, are kind of stair steps with aluminum. So as you know, aluminum always makes a 3 plus cation because it's a main group element. Walk down the stairs to zinc and silver and just do 3 plus, 2 plus, 1 plus. What I'm trying to say is zinc always makes a 2 plus. That's why in the name you don't see a Roman numeral, because it's well known and everybody knows that zinc always makes a 2 plus cation. So even though he's a transition metal, zinc and silver, they don't have options the way that like iron or chromium or whatever has. So you just have to kind of know that zinc is always making a 2 plus. He's a 1 minus, which means that the formula for zinc chloride would be this. and iron. So that's just the element iron. So let's go ahead and balance him out. Like I said, you got your species on there, balance them out. Start anywhere you want. Okay, right now the zinc and the iron are looking good. So I'm just going to go to chlorine. I see 3 chlorines here and 2 chlorines here. So the only way to fix that, remember, is do a 3 of the 2 and a 2 of the 3. So that gets me 6 chlorines on both sides. So chlorine's looking good. Now let's just kind of go to whoever we see next. Okay, I see iron. There's 2 irons, 2 iron atoms total on the left side of the equation. How do I get 2 irons on this side? Well, I will just put a 2 right there, and that fixes that. And then let's do the last one is zinc. So you just have to kind of check every type of atom. Zinc, there's 3 zincs here, 3 zinc atoms. Because if this is the chemical species, but I've got 3 copies of it, that gets me 3 zinc atoms, and that would put a 3 right there. And then just take a step back, make sure it's balanced, and it is, and then it's done. So that's kind of the next level of just turning these chemical species into like chemical equations, or chemical, like the description in a sentence form, turning them into balanced chemical equations. All right, so now that we have some good practice with that, let's kind of enter in the next topic here, which is reaction stoichiometry. So let's see here. Let me pull out my notes here. Okay. So reaction stoichiometry. Stoichiometry is a very intimidating word because we don't use it in like normal English language, but it's a very simple concept. It's not a difficult concept, and most students master it pretty easily. But what does it mean? So let me give you what reaction stoichiometry really means. Reaction stoichiometry is the area of chemistry that deals with the quantities of reactants that are consumed and or, I mean, you really can focus on anything in the question, and or products that are formed during chemical reactions. Okay, so this is a very practical side of chemistry. So let me go ahead and actually put up a chemical equation. Let me actually do one that we just had up there. Nitrogen reacting with 3 hydrogen to produce 2 ammonia. So reaction stoichiometry is going to be this type of question. I'm in the lab. I'm trying to produce ammonia. I've got nitrogen and hydrogen. If I mix them together, I expect to make ammonia. I'm simplifying this, but that's just generally the idea. Reaction stoichiometry is this concept. If I want to make 10 grams of ammonia, because I'm producing it for some reason, if I want to make 10 grams of ammonia, how much reactant should I start with? Like, it's kind of like cooking. How much do I need to make this much? That's the type of idea that we're getting at with stoichiometry. It's this practical side of chemistry. You're trying to make a certain product or whatever. Another way of looking at it could be something like this. I'm trying to make ammonia. I have half a gram of nitrogen in a beaker. I mean, I'm simplifying. How much hydrogen should I add to it to be the perfect amount? You know, I mean, I could add as much hydrogen as in the world. It's going to be way too much. But what would be the perfect amount? That's kind of like the concept of stoichiometry, that I need to make this much to make ammonia. So that's kind of what we're getting at here. So let me give you kind of how to frame this in your mind. So this is you. When you're reading this chemical reaction, okay, there's really 2 ways to kind of think about the coefficients. Okay, remember this means a 1. Okay, so I'll just put a 1 there for now. There's kind of really two like ways to read it, like doing a thought bubble here. One way is to say 1 molecule of N2 reacts with 3 molecules of H2 dot 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 to produce 2 molecules of ammonia. That's true. On a molecular level, if you had like, I'm just going to draw the little molecules. If you had a nitrogen molecule, nitrogen, okay, this is just 2 nitrogen atoms, he would need 3 hydrogens. Okay, there's 3 of them. I made them smaller because they happen to be smaller. He would need 3 hydrogen molecules. Okay, and if the chemical bonds broke, just like Legos, you break them and then you put them with new guys. If you had 1 of them and 3 of them, you would end up with 3 NH, or sorry, with 2 copies of NH3. Okay, you can kind of see I still have 2 of the larger atoms. That represents nitrogen. And I have 6 hydrogen atoms. They're just deposited, they're just combined with new things. That's what a chemical reaction really is. You just combine the atoms with new partners and you make new chemical species. So you can think of the coefficients as the number of molecules. In theory, that's, it's true, okay? But in reality, we don't do chemistry 1 molecule at a time. When you combine beakers of stuff, there's not just 1 molecule in there, there's bazillions of them. So in reality, that's not usually how most people read chemical equations. Instead, when you read a chemical equation, what you would normally say is 1 mole of N2 reacts with 3 moles of H2 to yield 2 moles of NH3. In other words, the coefficients are the number of moles required for each species to make whatever you're trying to make. Now, if that seems weird, because again, a mole is not something that we use in regular language. When we learned about the mole in a different video, we said it's very similar in concept to the word dozen. Anytime that you could use the word dozen, you can use the word mole. It just counts for a much bigger number than 12. It's just 6.022 times 10 to the 23rd. So let's think about it for a minute. Could we use the word dozen? Is it true that if I had 1 dozen N2s, that means 12 of them? Isn't it true that I would need 3 dozen H2s? I would need 36 of them. Let's back that up again. Can I say the word dozen? If you had 1 dozen N2s, 12 of them, you would need 3 dozen H2s. That would be 36. And you would get 2 dozen, 24, ammonias. So the fact that I can say dozen means that I can say mole, okay? It's just a bigger chunk that you're dealing with. It's a more rational number to deal with practically if you're doing lab work. All right, at the end of the day, that's the key point of stoichiometry, is that when you look at the coefficients of an equation, you say the word mole with them. 1 mole of this reacts with 3 moles of that to make 2 moles of that. Now, let's go ahead and applicate this to like how this works out to like practice questions here. Let's go ahead and say, let's say how many moles of NH3 would be produced when, let's go with 4 moles of N2 fully react. All right, so what this is saying is that I have 4 moles of N2 in a beaker. This reaction happens. How many ammonias will I get? Well, it's like, you can think of it like a ratio thing. If one of these produces 2 of these, then if I have 4 of them, I will get 8 of these. Are you with me on that? Now, here's the reality of it though. That was pretty easy when we use easy numbers like 4 or whatever, and when we have a 1-to-2 ratio. But when you have something like a 3-to-2 ratio, I will tell you, it gets confusing. Even for me, sometimes I will mix up what I do with the 2 and the 3. And forget about if you've got a 4 and a 5, or like a 5 and a 7. It can get very confusing. So I really think it's essential that you use a problem-solving technique that you can rely on, that you're not going to get tripped up in your brain. And that's how most people end up doing questions like this. Instead of just rationalizing it out in their head and thinking, oh, well, one of them makes 2 of them, so it would be double. Okay, that's fine for easy numbers, but it gets harder when the numbers get harder. And like I said, the ratios, they can get confusing too. So what I would recommend you doing is learning the technique for a reaction stoichiometry that I'm about to teach. And by the way, everybody does this. Everybody in chemistry does this. Everybody does this. So don't skip it over, and you got to trust me. This is what everybody does, and you should too. Let me tell you something right away here. When you are looking at a question and you have info about one chemical species, you notice in the question, the only number is 4 moles of N2. I have info about nitrogen, but what is my question about? My question is about ammonia. Question about someone else. Do you see the pattern here? If you're given info about one guy, but your question is about a different guy in your chemical equation, that's when you are doing stoichiometry. It's important to notice it. That's when you're doing stoichiometry. Info about one guy, but the question about someone else. So how do you accomplish it? Well, whatever number is in the question is always where you start. Okay, there's no other place to start, and we're using dimensional analysis. Everybody does, and you should too. You always just start with whatever number's in the question, especially if there's only one number, that's always where you start. So 4 moles of N2. And what you're going to do to accomplish this question is we need to figure out how many moles of NH3 are required. What you are going to use here is called a mole-to-mole ratio. A mole-to-mole ratio is very simple. It's literally a conversion factor. This thing here is called mole-to-mole ratio. It's a conversion factor that is built or constructed from the coefficients in the equation. Now, you're only going to use the ones that are relevant, okay? So we are trying to get rid of moles of N2, okay? So do you know, so because he's on top, we need him on the bottom. So this is what you would say. For every 1 mole of N2, you're just building the mole-to-mole ratio from the coefficients of the equation. And notice the verbiage that I'm using. For every 1 mole of N2, I will make 2 moles of NH3. And moles of N2 will cancel. This is your mole-to-mole ratio. And then this one we don't even need a calculator for. That will get me my 8 moles of NH3. Now I know that that's super easy, and almost everybody could have done that in their head. But the concept is important. Let's go ahead and show you where this is going to be, really, really useful. What if I had made the question a bit harder here? What if I said how many moles of ammonia would be produced when 0.975 moles of H2 react? See, now I'm stretching us a little bit because now the number is not such an easy number anymore. It's not 2. Or I guess it was a 4 before. So it's a little bit of a more complex number. And the species that I'm dealing with are H2 and NH3. Okay, see, this is a 3 and a 2, which is a little harder than a 1-to-2 ratio. It's a little bit more abstract. But you still solve the problem the exact same way. If you know how to do mole-to-mole ratios, it's not a hard thing to do. There's one number in the problem, 0.975 moles of H2. Oh, by the way, it is essential that you don't drop the moles of who, because we're about to pivot to a different chemical species. So you can't just write moles. You're going to forget who in the world you're talking about. So if it's a stoichiometry question, you absolutely have to keep moles of who. That's relevant, because that's going to help you figure out how to set up your mole-to-mole ratio. Now, we need moles of H2 to be on the bottom, so it cancels. Let's build the mole-to-mole ratio that is relevant to the question. For every 3 moles of H2, I will make 2 moles of NH3 because I'm trying to solve for NH3. That was what my question was about. Moles of H2 will cancel, and I'll go to my calculator. 0.975 times 2 divided by 3. And by the way, I just press enter in between both of those. I'm getting 0.65 in my calculator. Now, in terms of sig figs, so sig figs are going to start to become more and more important. This is a multiplication question. So the sig figs in your answer are determined by the numbers that went into the multiplication. This number has 3 sig figs. Those 3 are significant. That 0 is a leading 0, and it is not. These are what you call exact numbers. They're not measurements. They're just, they're like exact numbers, just, you know, dealing with the numbers of each molecule that you need. So those don't play into sig figs at all, which means our answer needs to have 3. Now, even though my calculator deletes the last one, that technically you would have to put back in there. That's your third sig fig, and it would be moles of NH3. So that would be the answer. All right, so that's like level 1 of stoichiometry. Let's extend it to really a little bit more typical level. Where you're not starting with moles per se, but you're usually starting with grams. Let me go ahead and put up a practice question that would be a good one here. So let's go with, how about, given this equation, so basically, if someone tells you that this is the reaction that we are analyzing, so cobalt reacting with perchloric acid, producing cobalt 2 perchlorate and H2. And I will tell you that unless the part of the question is balance it, most textbooks, myself, are just going to present it balanced. It's a good thing to check. It's a good thing to check to make sure that it's balanced. But unless they're actually telling you balance the chemical equation, most textbooks are not trying to trip you up. And if they present it to you already like this, it's already balanced. But let's check. 1 cobalt looking good. I see 2 perchlorates looking good, and then 2 hydrogen atoms looking good. So it's balanced. So here's the stoichiometry question. Let's see, how many grams of, let's go with, how many grams of hydrogen are produced when, let's go with 5.00 grams of perchloric acid react. Now, react fully. We're going to talk about limiting reactant and all that a little bit later, but it's implied that you get a full reaction, that it had enough time, that you had plenty of the other reactant, so that, you know, every little bit actually went through this reaction. So that's what was implied. All right, so one thing I want you to notice is that this time we're starting with grams. Okay, you got to pay attention to the unit. This is very essential. So you're going to write that down, 5.00 grams. But grams of what? Okay, it matters. It's grams of perchloric acid, which was this species here, HClO4. Backing up for a second, is this a stoichiometry question? Am I doing a mole-to-mole ratio? Well, let's see. I'm given info about perchloric acid. That's like what my information is about. What's my question about? It's about hydrogen. So once again, info about one guy, but the answer is going to be about another guy. That's stoichiometry. That's stoichiometry. Now, that means you're going to do a mole-to-mole ratio. Connect those dots. If it's a stoichiometry question, you're going to do a mole-to-mole ratio. Are you ready for a mole-to-mole ratio? Is this in moles? No. You can't do a mole-to-mole ratio because the moles won't cancel with anything. So how do we get a gram unit to become a mole unit? And in chemistry, that is beyond easy. And actually, frankly, so is going the other way from moles to grams. You need molar mass. Molar mass. That is your ticket. So we need the molar mass of this species here. So let's go ahead and figure that out. Oh, by the way, I've had this question a lot, and it's a great question. Do I need to think about that there's two perchloric acids? And the answer is no. Molar mass is sacred. Just find the molar mass of the molecule. So we're adding up one of the hydrogens. We're going to add a chlorine, which, let me grab my periodic table. Some of these I've got memorized and some of them I don't. 35.45. And we're adding 4 oxygens. That's going to be 64 total. So for the molar mass of this species, I'm getting 100.458. And I'm going to write it. Remember, molar mass, 100.458, is not just a number. It's the grams per mole. It is a conversion factor. It's just all about how do I use it. Well, this one I have to invert upside down because the whole point is I'm trying to get rid of grams. So I write 100.458 grams per mole. Now I'm going to rewrite HClO4 in there. I don't want to lose track of who I'm dealing with. Okay, that will get him in moles. Now it's time for your mole-to-mole ratio. You weren't ready for it back then, but you're ready for it now. The mole-to-mole ratio is where you pivot towards the question, towards the new species. So let's build it. For every 2 moles of HClO4, I will yield, and say this in your mind as you're writing, 1 mole, because if it's nothing, it's implied to be a 1, of H2. Notice moles of HClO4 will cancel. Now, am I done? Well, it depends. What's the question asking for? They want grams. Sometimes the question asks for moles, then you're done. But if it wants grams, you're going to have to carry this through. And by the way, let me back up a minute. I said when you're getting the molar mass, don't even consider that there are 2 of them. The reason is you're considering that there are 2 of them in this step. It's dealt with in the mole-to-mole ratio. You don't want to deal with it twice. Then you're kind of hit, double jeopardy type stuff. You don't want to do things twice. It will get you the wrong answer is what I'm saying. So molar masses are sacred. Just get them from the periodic table. Leave them alone. Don't change them because of coefficients. Now it's time for the molar mass of H2. Well, that's 1.008 times 2. So we need 2.016 grams per mole. And you can write H2 if you want. I mean, as long as you know what you're talking about, you don't have to overdo it. Now we're ready. This is the grams of H2. Let's see what our calculator reads. 5.00 divided by 100.458. Enter. I just press enter after every step. Divided by 2, because it's on the any number in the bottom gets divided by. Times, because that one's on the top, 2.016. And I'm getting, my calculator is giving me a lot of digits, but this number has 3 sig figs. Those are trailing zeros and a number with a decimal point. So my answer, because my molar masses have way more more sig figs. So this is going to be our limiting, significant figures. You always pick the one with the least sig figs, and he dictates what you get to report. So I'm getting 0.050. Well, it says 17, but I really need to stop with that digit there, and it bumps it up to 2. And the unit would be grams. I don't need grams of H2. Just plain grams is fine. Just like the first, main unit is fine. And there's my 3 sig figs. 0.0502 grams. That's how many grams of hydrogen I would get if I'm in the lab and I started with this much of that. So that's the practicality of stoichiometry. It's kind of giving you, helping you calculate how much you expect to make. Let's do one more, and I'm going to add one more layer of complexity on this. How about, let's go with, let me get a different chemical reaction. All right. Let's go ahead and pretend that we are doing this chemical reaction here. How about, let's go with Trying to see one that has kind of different coefficients, but that's fine. We'll just do this one. 2 AlBr3 plus 3 K2SO4 potassium sulfate yields 6 potassium bromides plus Al2 SO4 3. Okay, so I've got a balanced chemical equation. It's already balanced. So far, I've been writing all the practice questions as how much of reactant do you need to make product. But really with stoichiometry, you can relate anybody to anybody. So you could have a question that comes in this form. How many, let's go with grams of aluminum bromide are required to fully react with, let's put a little metric conversion at us here. So let's go with 25.5 milligrams of potassium sulfate. All right, so this one here, my info is about potassium sulfate. That's kind of what my starting number is about, potassium sulfate. My question is going to be about aluminum bromide. So it's stoichiometry, okay? Definitely stoichiometry, which means mole-to-mole ratios. So now we got to start. We got to start somewhere. Start with the number in the question. When there is only one number, you always start with that one. I will tell you we are soon going to do limiting reactant questions where you have two different numbers, and we'll talk about how to handle that. But there's no exceptions. If you see one number, write it down. That's your first number in your conversion. So 25.5 milligrams, but milligrams of what? Of potassium sulfate. So this just requires you to recognize that that's the species, potassium sulfate. That's the mass of potassium sulfate that we have in our beaker, whatever. We are needing to figure out the mass of aluminum bromide. Well, a couple things we have to do first. We are headed to needing to do a mole-to-mole ratio. We've got to do a mole-to-mole ratio. Clearly, we're not ready for a mole-to-mole ratio because that's not in moles. But it's not even in grams yet. See, we can't get it in moles unless it's in grams. That's the one thing that we can use molar mass for. So really, if you've got a metric prefix, the thing you have to do is just get rid of it. So in every 1 gram, there are 1,000 milligrams, correct? And that's all I would do just to get rid of it. Just get rid of that metric prefix. But don't put it in your calculator yet. Just let's set it up. And I guess you could write K2SO4 again, as long as you just kind of remember we're dealing with K2SO4. Now that we have it in grams, we can use our molar mass to get it into moles, because that's really what it has to be in for us to hit it with that mole-to-mole ratio. It's got to be in moles so they cancel. So we need the molar mass of K2SO4. So periodic table time. We're going to need 2 potassiums, and I would try to hit this all in your calculator. Just, 2 times 39.10, press enter, plus a sulfur, 32.06, plus 4 oxygens. Now, oxygen is 16, so just, you can do it in your head if you want, but 64. So the molar mass is this number, but remember, it's 174.26 grams per mole. So I write it like this, 174.26 grams per mole. Mole of K2SO4. Now that I'm in moles, we can pivot to the species that the question is about. For every 3 moles of K2SO4, I will need or react with 2 moles of AlBr3. And now I know how many moles of AlBr3 I need, but the answer wanted it in grams, and now from that I can just use his molar mass. Remember, molar mass of him because that's the species we're talking about right now, you know, at this point. If I use his molar mass, now I convert it to grams. I can convert it to grams. So aluminum and 3 bromines is 266.68, and I'm going to write it 266.68 grams per mole. Do you see why I wrote this molar mass as a right side up, but this molar mass as an upside down? It's just, you just do it in whatever way you're trying to, you let the unit that you're trying to get rid of tell you which way to do it. In this case, we were trying to get rid of grams, so we wrote it upside down. In this case, we're trying to get rid of moles, so we wrote it right side up. So see how that ends up being in moles. Or sorry, in grams as an answer. So now let's go ahead and get our final answer. 25.5 divided by 1,000, enter. Divided by 174.26, enter. Times 2, enter. Divided by 3, enter. Times 266.68. And I'm getting 0.026. And this has 3 sig figs. All the rest are not going to, this is going to be the smallest number of sig figs. So my answer will have 3 sig figs, 0.0260 grams, and that would be enough of an answer. Now, if you wanted to go ahead and put that in milligrams, you could. You could say that it's 26.0 milligrams. But I didn't ask for it necessarily in milligrams. As long as it's the right mass and like a reasonable unit, I'll take it. So that's fine. So that's stoichiometry. Now, in the next video, we will learn how to handle limiting reactant theoretical yield, percent yield questions, and we will start, we'll touch on a couple of little reactions that are in chapter 4. So, but that's it for today. Thanks for your attention, and hope you have a good rest of your day.